Okay, so hello again. Today we'll talk about experiments, hypothesis testing, and A/B split testing. It will be fun. So when you want to use statistics to prove something to yourself or others, well, you do some experiments, right? You get some sample data and you try to come to some conclusions, right? So first you think how you design the experiment. And it's like a separate discipline. You can Google it. So experimental design and analysis of experiments. There are different common designs, like a completely randomized design. Treatments, for example, medical test. Treatments are randomly assigned to the experimental units. Results may be affected by factors not accounted for by the experimenter. Like, for example, one group will become more like male and another group more female, or it's like different ages or something. So to account for this, people may use randomized block design and then compare results of treatments for each block separately, right? Factorial design, where you can check for a test for two or more variables. Analysis of variance and significance testing, so hypothesis test. Regression and correlation analysis, the residual analysis, graphical plots, correlation coefficient. Correlation doesn't mean causation. So what I'm doing here, I'm just very, very fast showing terminology which people may use in experimental design when thinking about the experiments. Time series and forecasting, monthly, weekly data, ARIMA, econometric models, and so on. Non-parametric methods when no assumption about the population probability distribution. So example, Wilcoxon signed rank test can be used to test hypothesis about two populations, and some other examples, whatever. Experimental design, statistical quality control, monitoring the quality of products and services, acceptance sampling, statistical inference. Well, this is what statistics is about, right? Using data from a noisy sample to make estimates or test hypotheses about the whole population. Sample survey methods, mail, phone, interview, sampling error, probability sampling methods, simple random sampling, stratified simple random sampling, cluster sampling, decision analysis. So you see a lot of ways you can approach problems, and I just wanted you to realize that, well, this is like a valid thing to think about. Next slide deck, I will talk about hypothesis testing. And hypothesis testing is a tricky thing, right? So here is a well-known example of regression to the mean. The idea is, so it's about designing experiments, right? So suppose you give a test to 100 yes and no questions to 100 monkeys who cannot read or answer questions, like, so they answer them randomly, and the results will be random. Most common score will be 50 out of 100, and the histogram will be bell-shaped, right? So it's a completely random situation. Then what you will do, you will take the worst monkeys who performed the worst in this particular test, and then you, I don't know, wait a week, and then you retest. And again, because it's all random, you again will get a random score of 50. So you will happily publish an article and saying that in this week, monkeys become like, monkeys improved, which of course is not true, but this is called regression to the mean. And this is an example of experiment which was not correctly staged, right? So hypothesis testing is an interesting area, and let's go for it. So purpose of hypothesis testing is to determine whether there is enough statistical evidence in favor of certain belief or hypothesis about a parameter value or a distribution. Okay, fine. And usually there are 4 steps. So you formulate the hypothesis, usually at least 2, called null hypothesis and alternative hypothesis. So for example, you're testing if the value is the same, null hypothesis, and then you may find an experiment that the value actually changed, right? So first you formulate the hypothesis. Second, you decide which level of significance we need, usually denoted as alpha, and usually it's about 5%. That's kind of accuracy you want. Step 3, select the test type and compute test statistics, like t-test, z-test, chi-squared tests, ANOVA test, binomial tests, whatever, multiple tests available. And after doing the tests, calculating your statistics, you're making a decision. People distinguish 2 types of tests, 2 types of errors, like in tests, type 1 error and type 2 error. And so this is kind of a table about it. So type 1 is a false rejection of a null hypothesis, and type 2, false acceptance of the null hypothesis. I want to stress about these tests that actually in the same experiment, depending how you define the null hypothesis, the type of the error may change from type 1 to type 2 or opposite. So here is an example, COVID test. And suppose we get null hypothesis 1, that person has COVID. So this is our null hypothesis. Then error type 1 is when the test says healthy on a sick person. So null hypothesis is that he is sick, and error type 1 when we say he is healthy. So we're rejecting a null hypothesis, and this is type 1 error. But if our null hypothesis is that the person is healthy, then error type 1 is when we say sick on a healthy person. So it's a completely different. You see that error 1 and error 2, they swapped. So you have to be careful so that people understand you correctly in choosing null hypothesis. Like, for example, in life, guilty or innocent. The person is presumed innocent until proven guilty. So null hypothesis is innocence, and we need to prove that he's not innocent. Sick, healthy, the person is presumed healthy. So null hypothesis, healthy. Airplane or noise, when we're trying to detect airplane, the signals are mostly noise, so null hypothesis, it is noise. And we want to prove that something which we see on the screen is actually not noise, and then we say it's a plane. Okay, p-value and null hypothesis. P-value, well, it's a probability value. It's a probability of getting results at least as extreme as observed. So suppose we have some sort of distribution, and this is our null hypothesis, null value, and we actually getting value somewhere here. Then, so the area under the curve, maybe it's a single-sided or two-sided test. So let's say it's two-sided. So area here and area here together. So if they are less than 5% of overall probability, then we're saying that, well, p-value is less than 5%, right? And if this is what we decided to do, so we're saying like, okay, if this less than 5%, so in 95% cases we're here, but what we actually see in the experiment that we're getting here, that means that we need to reject the null hypothesis, that the value that we're actually getting in the experiment is different from the null hypothesis, right? So p-value is used to estimate how improbable what you're seeing, right? So if, for example, we in experiment getting value like somewhere here, we say, Yeah, it's a little bit different from null hypothesis, but it's within like within error. So it's not a big deal. But if we're consistently getting big difference, then we're saying, yeah, the value is actually different. Okay, so p-value. Well, there is some terminology. So level of significance, I was talking about 5%. It's also called alpha or alpha. Confidence interval is like this area. So it's 1 minus alpha in area, right? Critical value is this value where we transition from keeping the null hypothesis to rejecting the null hypothesis. Z-score is simply the distance from the mean expressed in sigma, in how many sigmas, how many standard deviations we differ from the null hypothesis from the mean. And margin of error is amount of random sampling error in the result. So if we don't have enough data, then our margin of error will be pretty big, right? But then as we get more and more and more data, we get more and more precision to a certain extent, more and more accuracy. But then after a certain point, adding more data doesn't help. So this is a terminology related to null hypothesis. Okay, this example I believe I gave in previous lectures. So here's just example of understand the p-value. So the problem number one, we tossed coin 10 times and got 8 heads. Compute p-value of this outcome. So p-value again is probability of getting the data that extreme or even more extreme. So the null hypothesis, null like average would be 5 heads, right? But we got 8, which is kind of extreme. And to get p-value, we need cases where it is 8 heads, 9 heads, and 10 heads. We calculate the probabilities. Well, there are different ways how to do it. It's a binomial distribution. We can look at the table. We can use Python module. We can just run a for loop to test it like that. And we calculate the sum of probabilities of 8 heads and 9 heads and 10 heads. And we're getting this result, 0.055. So the probability is just a little bit more than 5%. So it's within our margin of error, right? Okay, I will not cover this. We already, I think, spoke about it. This is just example of direct calculating of p-value by just running experiment. So here it's 22 heads of 30 coins. So we repeat 10,000 times. In each trial, we generate randomly, we toss the coin 30 times, and we look how many heads, and if it is more than or equal than 22, we increase the counter. So 10,000 times we repeat this experiment, we calculate how many times we got result 22 or even more severe. Just a reminder, when we're calculating p-value, probability that event, okay, no, not here. P-value is probability of getting result at least as extreme as observed. So it means in this situation, 22 and more severe, which is like 23, 24, 25, and so on to 30, right? So, and that's the probability. So apparently the p-value is very small. That means that this event is quite extreme, like 22 heads out of 30. Okay, when you do p-value, you can do it using different types of tests and distributions, whether it's t-test or chi-square test. We haven't actually covered them in this cycle of statistical lectures, so I will simply skip it for now. Also want to show you that there are some Python modules which you can use in SciPy. Okay, I'll just skip that for now. checking whether coin are fair using t-test or using chi-square test. There are more examples which are listed here, which also I want to just skip. The dichotomous use p-value in statistical inference is worse than useless. Okay, I copy-pasted it from one discussion, and I guess this is too deep again for this lecture. So p-value is conditional probability. It has probability of data given null hypothesis. But what we want is probability of null hypothesis given data, right? The calculation of p-value depends on at least three things: the effect size, the uncertainty level, and sample size. It is a standard result in statistical theory that based on one set of sample data, we cannot tell the observed effect size is due to treatment or due to random variation. It has sampling distribution requires to repeat the same experiment many times before confirmatory conclusion. If by nature null hypothesis H0 is false in the majority of cases of real data research questions, p-value is 0. Okay, in summary, p-value based null hypothesis significance test is logically not defensible, technically flawed, and practically damaging. I really love it, like the way he wrote it and explained it, and well, it's true, but well, still, everybody is using p-testing, doing p-test hacking, and all other like cruel things. Anyway, this is a medical test paradox. So we have 1,000 people, 1% of them has a disease. So number of sick people 10, healthy 990. We use a test with sensitivity 90% and specificity 91%. So we think it's pretty good test, right? So sensitivity is recall how many sick people we actually discover using this test. So 90% of sick people, and specificity is the opposite, right? And the interesting thing is, so this shows like this situation, and then given that the test shows positive result, a disease, what's the actual chance of a person being sick? And the answer is it's about 1/10. So, so test shows that it's sick. It doesn't really mean that he's sick. That's in practice what people do. They then use another test, second test, maybe more expensive test. Okay, this is example of a drug test. This is some real curves. Okay, this is end of this slide deck, and I want to talk about A/B split testing. So this is interesting. First of all, where it came from. Claude Hopkins wrote a classical book, Scientific Advertising, a long time ago, like 100 years ago. Why it is so famous? Because he introduced a scientific approach to advertising, where you invest money to run ads, and then you calculate the results. So you use some analytics, you do some statistics, and then you test which advertising works better, right? So I guess probably that's where the terminology came from. A/B split testing was pioneered in early, like again, 100 years ago, by William Seeley Gossett, which is known as student. So he worked with Carl Pearson in London, and so they developed this test to compare results of two groups for small sample sizes. Okay, importance of A/B split testing. In 2012, Microsoft employee working on the search engine Bing created an experiment to test different ways of displaying advertising headlines. Within hours, the alternative format produced a revenue increase of 12% with no impact of user experience metrics. So today, companies like Microsoft and Google each conduct over 10,000 A/B split tests annually. It's ongoing, it's always, it's multi-factor, it's automated. You have to do it. If you don't optimize your advertising or whatever, your platform, you will lose to competitors. So A/B split testing is a must. So usually you have let's say we're talking about web page. We have one page which was already tested well, and it's called control. And then you try to make some variation of this test page, change something, and then you compare them. A/B split test. Okay, so here is an example. So let's say you have A, and you have some distribution of results for A, and then you have B, and you want to find if B actually better or not. So if A or B, if they are different. And well, in this case, it looks like we have something like normal distribution, and we want to separate them. We want to get at least like like here. So here you can clearly see that they're separate. In order to achieve that, you need to make them narrow. How you make them relatively narrow? You increase number of your data points, and as you increase number of your data points, the error decreases as a square root of n, right? So given the distance, you can estimate how many data points you need in order to like see separation and then be able to say if they are different or not. Okay. Non-Gaussian distribution. So here, all this is only for Gaussian distribution. But in real life, you will have non-Gaussian distributions. And here is an example. So this is test A. And suppose this is, I don't know, number of clicks on a page. And this is A, let's say this is control, and this is B. And they look very, very similar. And just looking at them, and they're random, like if you repeat the test, they will look a little bit different. So it's difficult to say if they're statistically like different or not, if whatever improvement you designed worked or not. So one of the ways to test it is well, you can do sampling, you can convert it to normal distribution and then apply regular tests. But a much simpler approach is to do shuffling. And I think I spoke about it at one of the lectures. The idea is you decide on a null hypothesis that A and B are actually the same, right? And then you combine them together, and then you start randomly select half of the points, and so randomly split in two halves, and then you look at difference between the means of A and B, right? And you repeat it. In this case, you repeat it like 5,000 times. What you end up having, you will end up having a distribution of differences, and then you will ask the question where the actual difference I've seen in my experiment, where it goes on this distribution of differences. So is it in the middle? Then it means they're not different, or it goes to the side, and then you can apply your 5% test criteria. So this is reality. This is what people do in reality. People use null hypothesis that they're equal and then use shuffling. Okay. 8 common pitfalls of A/B split testing. Ending the experiment prematurely, not getting enough data points, not consistent, not truly random cluster assignment. Random assignment fails to distribute heavy users equally. Okay, fail to check what is called ceteris paribus assumption, all other things being equal. Okay, cross-contamination between treatment and control groups, get fooled by false positives while making multiple comparisons. Individual and aggregate patterns look different for ramp-up experiments. So it's a Simpson paradox, and here it is described. So in this experiment, it looks like it grows, and in this experiment, it looks like it grows. But actually, you can see that, like a big picture, that it goes down. Fail to check the primacy and novelty effects. That meaning that, for example, you're testing a group, but one group are old users and another group are mostly new users who never seen this page or something like that. Okay, bias. You need to make sure you are comparing apples to apples. Buckets should be the same size, same composition, only include people who could have been affected. A/B split test may give different opposite results for different segments of your population. Interesting. Okay, interference between A and B. Okay, one-sided market, two-sided markets, how to avoid interference, identify clusters, ego cluster randomization, like in LinkedIn, measuring the one-out network effect, meaning the effect of a user's immediate connection treatment on that user, then each user either has the feature or doesn't. Geo-based randomization, time-based randomization. Okay, so it's a science. Novelty and primacy effects. When there is a change in the product, people react differently. Some people welcome changes, and some people don't like the changes. Okay. Multiple testing problem, multivariate testing, and so we run multiple tests. So this is Bonferroni effect. We spoke about it before. Okay, I actually want to finish on this because we were ready for half an hour. So I'll stop the recording.